my original topic, that is audio and speech, and how I combined the idea of RWDC, real-world data circulation in audio system. That is the topic of this talk. Okay. And particularly for the 3D audio services, I don't know how much of you are familiar with the 3D audio. 3D audio is the audio that gives you a spatial sensation of the sound. So anyway, this is a 10-year research history of my group. So I hope you like this. The topics are like this. I like first, I briefly introduce about the spatial audio technology. And then I will little bit go in detail about what is the elemental technologies for 3D audio. Those are blind separation of combined signals, and also how we can give you a spatial impression to the sound. And then this is the very interesting part of this talk, short history of SLP audio at our laboratory. And then I'm talking about how can we incorporate the idea of real-world data circulation in that system, and then that is I guess conclusion. So first of all, in general audio system is like this. So from the days of the analog record disc, that was not changed. That is the combination of microphone and amplifier and loudspeaker or headphone, whatever the sound sources. And we can simplify the idea is like that. We capture the real world acoustic signals, which has the spatial characteristics, which mean that the acoustic sound pressure is different across the measuring points. And you use usually microphone or microphones or array of microphones, and then you convert it into electrically disk or silicon memories, and then you're gonna play back that signal as if you are listening to that sound in the particularly same field or same place in the where you recorded that sound. And we usually or used to use the loudspeaker as the primary source for the sound production, but currently most of people use the headset, like me. So things are changing, and also the media for recording and storing music has over very much changed, like analog discs to the silicon audio. Silicon audio means that everything is digitized into the memory, and then you can download from the website and play back it on your smartphone or things like that. So whatever those medias are, the basic structure of the signal processing is not different. And for a very long time, we have believed that the good audio system can reproduce the same signal that you captured at the field. So this and this should be, as close as possible. That was the good audio at that time. And spatial audio is a little bit a different idea. You will add a new, you try to add a new sensation to the sound so that you can feel like this, big hall, theater hall, which has a good reverberation and a good reflection sounds in the appropriate direction. Actually, the goodness of the theater hall, they say, is decided the direction of the sound coming from the stage particularly the late reflection sound are said to be very important for the goodness of the sound sensation. But anyway, I'm adding these, how do I say, spatial impression is the elemental key issue of 3D sound field and audio systems. Then the system not such simple. We need to modify the original sound in order to give you another impression of the sound. This is another part which we have developed for a long time in order to realize the 3D sensational technologies. And we called it selective listening point audio because the famous professor at that time, Professor Tanimoto, some of you may know him, called his virtual, how do I say, they invented or studied about selective viewpoint. Am I correct? Selective viewpoint TV or free viewpoint TV. Yeah, he is also doing the same kind of things for image. He tried to capture a lot of ray of the sound, not sound, but the light, and reproduce it in an appropriate manner, which was invented by Fujisensei, actually maybe, to generate the scene, arbitrarily scene, if you are there, by based on the very simple signal processing, and they call it free viewpoint TV. So we named this technology selective listening point audio. Not free, but selective. But the meanings are quite the same. And this what we call SLP audio. And what are the fundamental technologies for the SLP audio? There are two fundamental technologies. One is signal separation, because whatever you record the sounds, the recorded sound signal is a combination of different signals. Maybe, for example, if you record a classic concert, your recording contains a lot of music instrument signals, because the sound field is the additive field, which means that the sound pressure due to the different signal sources are superimposed into one signal. And if you measure the sound pressure as a time sequence at a particular point through the microphone, then the microphone signal contains the sum of several sound sources. So suppose you have a saxophone here and a violin here, then what you record would be the sum of them, okay? So that's the one very important fact and point. And in order to change the locational sensation of the sound, we need to change the, how do I say, ratio in amplitude of each of two sounds, like this. So we like to change the amplitude of saxophone against to the violin. By doing that, we can change the spatial sensation. Of course, that is not enough. We need to also change the phase of the signal, but this is not mostly important things here. Well, mostly important thing here is we need to, estimate the independent two source signals. That is called the technology. That technology is called the blind signal separation. This is a blind because we only know the sum of two signals, which means that you need to estimate the original number, like 1 point plus 5, or 6 is equal to 3 plus 3. So no one knows how the number 6 is consisted of without any subsidiary information. But blind source separation try to do that based on the reasonable assumptions on the signal sources. Okay, but anyway, in order to separate two signals from the recording, we need to apply some, complicated technologies, signal separation. That is the first one. And the second technology that we need to develop is the way to give the spatial impression to the sound, each individual sound, X1, X2. That cannot be easily done by simply changing the amplitude of that. We need to do different things. But I'm gonna talk about it later. So the basic theory of signal separation would be, how do I say, in favorite topic, has been favorite topic in, say, 10 years back. I guess after the first neural network movement gone. But it is a very interesting topic. Mathematically, of course, there are several implementation or representation of signal separation method, but this is the most classical and straightforward way. Suppose that you have two signals, x1 and x2, and you describe it as a vector x. And by combining two signals, you will have several signals. For example, suppose that you have matrix A here, like here. Sorry, I need to write down a more appropriate place. Okay. So we have signal X. Oops, sorry. Just not pen. X1, X2, and suppose that you have one matrix. Then the result of operation of matrix this A11 times X1 plus A12 times X2 and A21 X1 plus A22 X2. So you can describe the mixture of signals in terms of the mixture of in terms of the set of vector for another combination or linear combination of them, which means that if you have two microphones and capture these signals by microphones, then the estimation of the saxophone and violin becomes the problem of finding the inverse matrix of A. Right? So this is very, very simple problem for if you knew the both of them. Of course, you do not know this. Therefore, you need to have some assumption to identify what is A or what is the inverse of A is. And the most earliest work try to solve this problem based on the independence of each individual signal. They assume that the violin and saxophones are independent, which means that the mutual information value of two stochastic variables are very low. Okay, what did it say? Mutual information, mutual information, is it low or high if they are independent? If they are completely independent, then the mutual information must be high, right? Sorry. I is equal to hx minus hx y, which means that they are completely independent. Then this is hx. Therefore, this should be minimized. Okay. Right? I'm sorry, this is our slide, so we need to minimize the mutual information between X and Y. I'm sorry, this is a slightly complicated story, but the important thing to know is that without assuming some sort of relation or characteristics of the source signals, we cannot solve this problem. And very early stage of the assumptions are that they are independent. I mean, violin signal and saxophone signals are independent. Therefore, try to find a matrix H that would be that so that the H minimize the mutual information between two signals. Then that matrix would be good estimate of the inverse matrix of mixture. And then you apply this mixture, a mixture matrix, and you can get independent signals, saxophone, violin, even if they are combinations of the signals. Okay. So this is one demonstration of such technology at our laboratory. Sorry, this is Japanese captions, but sounds are sounds. So they speak Japanese also. So this is a technology using the small microphone array that will be introduced later. And there are 4 male and 3 female speakers. Here's a mixture of sounds captured at the small microphone. And try to, separate each speaker's sound. So this is the technology developed probably 10 years back. You saw, sorry, I don't know, but so signal separation has been studied more than 10 years, or still, it is a very hot topic of the signal processing area. But almost 10 years back, we have built this kind of technology. Not 10, 8 years, maybe. Therefore, the signal separation was sort of a usable method for us to build SLP kind of things. The other topic or technology that is that is indispensable for building spatial impression sound audio is the HLTF, or the technology so-called the transaural audio. Why do you know why people can perceive the direction of the arrival of the sound? One big cue is the difference of time. You perceive the difference of the arrival time. Because, for example, the sound source is located in your right-hand side, then your right ear will get the signal for earlier than left ear. So in your brain, will do the signal processing, comparing the two difference of the two signal phases, and then you can perceive somehow difference in the location. Of course, another big cue is the intensity or sound pressure level. If the sound is here, then obviously right ear perceive a bigger sound than the left ear. So those differences of the signals at the left and right ear would be processed by your brain, and you feel the difference in a location. That is the one big aspect of the spatial audio sound. And it is called ILD and ITD. ILD is the interaural level difference, and ITD is interaural time difference. Time or the phase of the signal, if it is a simple sinusoidal signal. And the other big topic of this area is HLTF, head-related transfer function. Do you know why you can perceive front and back in sound? Because suppose that there's a sound source here or there. The arrival time and the intensity are identical at the left and right ears, which means that you cannot discriminate the position of the sound source from this and this. That is the fundamental difficulty of changing only this part. But because we have a pinna, jikai, and your head shape is not completely symmetry, which means that the sound propagation or sound arriving path to your both pinna and your ear canal are slightly different when the sound source is in front and in the back. So those things are very useful to make you feel like the sound is coming from the particular sound location. Those transfer function is called head-related transfer function. And by fully utilizing these kind of things, when I was a junior high school student, it was a very big movement to record sound by using this kind of facilities. Here's a dummy head, and the microphone is imposed in our ear canal, and we record that sound like, for example, an locomotive train, and we record that, and they sell it as a commercial disc, and people buy it to listen to the locomotive sound of the locomotion in a good feeling. So I was such a good boy, actually, when I was a junior high. So I bring my tape recorder, which was very, very expensive at the time, made by Sony, and bought a stereo microphone and get on my bike and record the sound of the, waterfall or things like that. But anyway, these spatial impression audio technology was very popular at that moment, 30 or 40 years back. But currently, no one pay attention to that. I found small, clips on a YouTube, which uses almost the same thing, but operated by a funny girl, and her breath or things are recorded by these kind of things. That's a funny side. But anyway, using these technologies, you can feel as if you are there in the sound field. Okay. So this is a typical HLTF head-related transfer function that I mentioned. If you have directivity to the particular sound location, in this case, maybe it is almost in front, then the sound you hear is not the sound that played at the speaker. You have dips here, there, and there. I guess this is the 20 kilohertz spectrum range, but you have several dips due to the complex shape of the pinna and also the hairs or things like that, which means that these dips are function of the your physical shape. Therefore, if the sound location will be changed, then these dips are changed. And of course, these dips depends on the personality. Therefore, this is a personal dependent function, HLTF. Therefore, this function is not a function of only F, but also theta. That is the arrival angle. So in order to build this function, we need to measure the actual transfer function for each individual That is not an easy task, but we can interpolate or generate based on the several rules, which is built by measuring more than 100 subjects of HRTF. We measured more than 100 subjects of HRTF, and we disclosed it through the internet. At that moment, that site was very popular for the researchers because that was the world unique numbers of the HRTF data set. Combining these technologies, once you have recorded several sounds of the mixture of sounds, then you separate them and you add spatial impression in each individual sound source, which means that we can produce the completely different spatial impression of the particular same sound plane. That would be very interesting to me at that time. Not all students agreed with me, but several students agreed with me and tried to build such system together with me. So these guys are very active students at the time. For example, Salvatore, he invented a very smart way to apply signal processing for the blind signal separation. He's now a full professor of the University of Tokyo. Nishino-kun was expert at the time for building the HRTF function based on the measurement. And he's now still working together with us at Mie Prefecture, Mie University. And Kenta Niwa, he's a very unique guy. He was the first guy who built SLP, selective listening point audio, which makes the sound impression of the moving instruments. He's still working in this area at KDD, NTT Research Laboratories. And he shown up more than 2 times in World Business News, Toretama. So he's a very funny guy. So if you are taking my class in media science, he will be shown up in several weeks. But anyway, these guys built very nice algorithms and technologies for realizing the SLP audio. So this was the memorable. I'm not sure it was 2008 or not, but probably. So do you have any idea? This was the first one first video that Tanimoto Sensei brought this to the MPEG meeting to make his group survive. No? Okay. So this was a very, very impressive video. So let's see. So I don't believe you see what has happened, but usually, you clearly see that the scene is smoothly changing. That was the basic technology for the Freeview Point TV. We have several sets of camera and connect the image based on the angle, not simply connect them like a matrix, movie matrix, but they calculate the accurate image based on the technology. And we have also add the sound by generating the HLTFs and other stuffs based on our technology, so that the sound at that point or at that direction sounds appropriately for you. So if you use the headset, you better feel that kind of things. But by using very poor speakers, and I'm not sure these are a stereo system or not, it's not easy to perceive. But this was a very interesting video. And we bought a small Game Boy. I don't know, Game Boy, PC, I don't know, PS3, right? These kinds. Eh? PSP, yeah, PSP, 4 or 5 PSPs, and we put this media in that, and Tanimo Sensei brought that to the MPEG meeting, and by doing that demonstration, his group was survived in an MPEG whole structure. So this is a very intensive work with me and Tanimo Sensei's group. So the secret of this system is very, very complicated. We have used a huge number of cameras and microphones surrounding the old players. Of course, the numbers of the camera are discrete, not infinite, of course, but it is. There are many, like 7 or 10 cameras or more. Here's a camera unit. Actually, this is a place that you are, using as a leader studio, actually. So these experimental facilities were located in the, 6th floor of the west wing of IB building. And we have a lot of microphones here and there and surrounding the players. And we got more than 30 or 40 channels of sounds and use those signals for separating the original signals. So here's another demonstration that only for audio, but we brought this to the ICASP. It was very interesting memory. For example, this is the sound. So this is set up by experiment. Okay. So we use 6 parts of instruments, and each of them consists of Jupiter sound, a Jupiter music clip, and when we play back them at once, then the signals that you capture, for example, this location would be something like this. No, we don't have that. But we have that. We have on stereo. No, I'm sorry. So of course the sound you capture are differ among with each other. Depends on the place. And by applying the signal separation technology, we can, estimate the original source like this from the, combined signals. This is the signal separation, and by applying the special impression, for example, assuming that the listener moves from here to there, then we can build a new sound. I don't know how much you feel about the, reality of the sound, but this is a nice example of the SLP audio for us. And we have improved the system from using this sort of a surrounding microphone system to a small dodecahedral shape microphone that you saw in a video clip. And this was the first interface for controlling the SLP audio. User tried to move these things based on the mouse. And you can drag and place the mouse somewhere different here. Then you are hearing sound, simulate how do you listen at that point? So that was SLP point. So we have realized SLP audio based on that. But sorry, I need more than, I need 10 minutes more, sorry. But this is not enough because the listening impression is not always good for the particular person. So if someone built this particular listening point, and but he liked that point, but another guy do not like that point, things like that. So we need to impose some system to specialize or to adapt to the particular person, and that is really making a loop. The guy need to have a circulation. So that is the circulation. What I like to talk in this topic, so that they can change the auditory impression of the generated sound field, and that is not general for everyone, but that is special for the particular person. Therefore, we need to build this circulation for everyone, and by doing that, we can collect the distribution of the sound, distribution of the preference of the users who use this system, and how many people like to listen this sound here and there. So this is the circulation, and that we are now developing the part. And the key issue is how to design this volume to change the difference of the sound sensation. But unfortunately, I do not have enough time to talk about that. So I just suggest 3 things. That the interface should be work real time, therefore, which means that if you change the volume, then the sound should be simultaneously increased, which means in this case, if you change the volume, then the sound sensation of the locational audio should simultaneously change in a consistent manner. That is a very important point. Second one should be intuitive, right? So that the continuity of the controlling should be preserved. Otherwise, you cannot, imagine how can you, operate that button. So this is actually a very important point that I suggested to Nagai-kun last night. If you do not know how to control the system, then the circulation would not work, right? Would not work appropriately. So we need to have such an intuitive interface for applying this circulation for the human. And final thing is the engineering thing. We need to use a lower complexity system. Otherwise, we cannot control because there are too many parameters to be controlled. So for example, for the spatial control case, we need 2 times n, which n is the number of the sound source, freedom for controlling the sound source location, right? And it is natural to use 2n slide bars, but you cannot control such a huge freedom of the system. Therefore, we need to convert this into one single slide, and that is now, we are now trying to solve this problem, and that can be utilized, solved in several ways, but I skip it. And currently, we are now having this kind of a demonstration, which has been built by Otani-kun. He's an RWDC of this system. And if you turn this knob, then the location of the instrument will be changed, and you can perceive. You can enjoy the. Different sound sensation. So image and sounds are not. So image and sounds are not synchronized. Sorry, but you see the different location of the balls according to the sound intensity as you turn around the knobs. Therefore, you can choose the optimal sound location for your purpose. I'm sorry, your sound is very terrible. But this is based on the particular technologies that we have developed for these purposes. どうしてかな I believe it should be moved, but anyway, this is the final slide. So please understand that simply applying that high technology to do or to enable something is not sometimes very is not enough for very good services. But improve the services by the user themselves and make a loop to feedback those improvement done by users into the system must be very, very important for deployment of new technologies as user favorite services. And currently we are building this system on a smartphone base. And actually, he's now working in NTT Lab as an intern student, and they are, building such system. And sooner or later, I guess it will be more than not will be longer than 2 months. You're gonna see a real small device, which you can see more interesting, funny visual interface as well as the sound reproduction systems. And I believe that that's going to be a very good commercial product in several years. But anyway, thank you very much for listening, and sorry for using more time. If you have any questions, I'm ready to answer. Otherwise, thank you very much for coming.